Bismillahirrahmanirrahim. Today we will cover lecture number 19 of Mechanism of Material 2, and in this lecture we will discuss about Castigliano's theorem, basic understanding and its derivation, and then the deflection and slope of beam by this method, Castigliano's theorem. So Castigliano's theorem, in 1879, Albert Castigliano, an Italian railroad engineer, published a book in which he outlined a method for determining the displacement and slope at a point in a body. This method, which is referred to as Castigliano's second theorem, applies only to bodies that have constant temperature and are made of linear elastic material. So these are limitations: constant temperature and linear elastic material. If the displacement of a point is to be determined, the theorem states that the displacement is equal to the first partial derivative of the strain energy in the body with respect to force acting at that point. That is important, at that point, and in the direction of displacement. And direction should be in direction of the displacement. In a similar manner, the slope of the tangent at a point in the body is equal to the first partial derivative of strain energy in body with respect to couple moment, displacement with respect to force. But for slope, partial derivative with respect to couple moment acting at the point. The point means at that point where it is required, and in the direction of this slope angle. This theorem considers a body of arbitrary shape which is subject to a series of n forces, P1, P2, Pn, arbitrarily different forces are being acted. According to conservation of energy, external work done by these forces must be equal to internal strain energy stored in the body. So external should be equal to internal. However, the external work is a function of external load. External work is function of external load like this. U A is equal to summation integral of P into dx. So the internal work is also a function of external load. Thus, Ui is equal to Ue, also a function of external load. Now, if one of the external forces, say Pj, is increased by a differential amount dPj, the internal work will also be increased such that the strain energy becomes, so dP is increased, then strain energy change will be like this, dUi. So due to this dPi, so Ui, internal strain energy, plus dUi is equal to Ui. Initial was same, but dUi is equal to partial Ui over partial Pj into dPj. Actually, that is displacement, and this is force, and product is energy. This value, however, will not depend on the sequence in which the n forces are applied to the body. So it is irrespective of sequence, whether we apply first force, then dPji, or first differential Pj and then these load. So it is not depend on sequence. For example, we could also apply the increase dPj to the body first, then apply the loads P1, P2 and Pn. If we do this, dPj should cause the body to displace a different amount d delta j in the direction of dPj by equation U E is equal to half dj into delta j. P is force and that is displacement. So half is taken because it is linearly from it is increasing from zero. Actually, this is energy. The increment of strain energy would also be that is external energy. Then increment would be this is internal or strain energy, and it is half dPj into d delta j. This is a second order differential and may be neglected because it is very this is small, this is also small, product is, so it can be neglected. Application to the load P1, P2, Pn causes dPj to move further through the displacement delta j, so that now the strain energy becomes Ui plus dUi is equal to Ui plus dPj into delta j. Here Ui is the internal strain energy in the body caused by the load P1, P2, Pn, and dPj delta j is the additional strain energy caused by this differential force dPj. To summarize a question that was previous, this one, and this represent the strain energy in the body determined by first applying the load and then dpj. First applying the load, then dpj, that is this equation. I'm saying previous equation here. And equation this one represent the strain energy determined by first applying dpj and then applying load p1 p2 pn. Since these two equations must be equal, we require, if you compare this equation with this equation, it should be equal to this one. Dpj is equal and remaining is delta j, and that should be equal, delta j is equal to partial dui or partial pj, which proves the theorem. The displacement delta j in the direction of pj is equal to the first partial derivative of strain energy with respect to pj. So that is theorem. If you take the partial derivative of strain energy with respect to load applied, it will give you deflection. Castigliano's theorem applied to beams. The internal strain energy within a beam is caused by both bending and shear. But shear will be neglected when the beam is long and slender. So, however, if the beam is long and slender, the strain energy due to shear can be neglected compared with that of bending. So we will take bending and we will neglect shear if beam is long and slender. Assuming this to be the case, the strain energy is ui is equal to integral of m square dx over 2 ei. Omitting the substitute I, Castigliano's second theorem, delta I is equal to partial delta ui over delta pj becomes, when you omit this script, so delta, that is deflection, is equal to curly over curly p integral from 0 to L, that is the length of the beam, into m square dx or 2ei. It is dx, not d raised by dx. Rather than squaring the expression for internal moment, integrating and then taking the partial derivative, it is generally easier to differentiate prior to integration. So for deflection, delta is equal to, so if you take, first of all you take the derivative, then take the integral, it is easier, and that is it. So we will apply this formula for deflection. So deflection delta is equal to integral from 0 to L into m into curly m or curly p into dx over ei. Here, delta displacement of the point caused by the real load acting on the beam, p an external force of variable magnitude applied to beam at point, and in the direction of delta, m internal moment in the beam expressed as a function of x and caused by both the force p and actual loads on the beam. Internal moment in the beam, function of x and caused by force and actual loads. E, modulus of elasticity of the material. I, moment of inertia of cross-sectional area calculated about the neutral axis. If the slope of the tangent at a point on the elastic curve is to be determined, the partial derivative of internal moment with respect to an external couple moment m prime acting at the point must be found. For this case, for slope theta is equal to integral from 0 to L m into curly m over curly m prime. Here it is changed. It is m prime now for slope. For previous it was load p at that point, and here it is moment m prime at that point into dx over ei. So this we will use for slope. The above equations are similar to those used for the method of virtual work, except m and m theta replaced by curly m or curly p and curly m or curly m prime respectively. In addition, if axial load, shear and Taurian cause significant strain energy within the member, then the effect of all these loading should be included when applying Castigliano's theorem. So we can apply Castigliano's theorem by considering shear, Taurian and all other axial loads. To do this, we must use the strain energy function along with their associated partial derivative we have. So delta will be equal to summation n into curly n or curly b into L over ae for axial load plus integral from 0 to L fs into v curly v or curly b dx over ga shear plus integral from 0 to L m into curly m over curly p in dx over ei. Just we have done, that is for bending, plus integral from 0 to L t into curly t or curly p into dx over jg, that is Taurian. So axial, shear, bending, Taurian, all the effects are compared, are added up for overall effect. So that is the Castigliano's theorem. Now we will apply, and we will apply on very simple example. So Castigliano's theorem, we have to find that says deflection is y, that's what will be equal to this formula, integral from 0 to L m over ei into curly m over curly p prime dx. P prime is load at that point. If it is already given, then we will use that. If it is not given, then we will apply a fictitious load p prime at that point where deflection is required. So that is formula 1. So for slope, theta is equal to curly over curly m prime is equal to the integral from 0 to L m over ei curly m over curly m prime dx. It is equation 2. Cantilever beam having point load at free end, and we have to find the deflection only at free end. For that, first of all, problem is given. This is fixed end, this is free end, p load is already applied. So first of all, we will have a section 1 and this is our reference. From here to this section, distance is x, total length of the beam is L. So first of all, we will do this sectioning. So for section 1 we will draw the free body diagram of this section. P is applied, distance is x. So at this section point, at this section, shear force V and bending moment M will be applied, and this will cover the effect of this part of the beam on this section. Anyhow, applying the equilibrium condition, summation of all moment at section 1 should be 0, taking counterclockwise as positive. M is counterclockwise, that is bending moment, plus P into X, that is again counterclockwise, so plus Px equal to 0, and this is valid for whole beam from 0 to L. So if limit is other than 0 to L, then we should have another section. So M is minus Px. To apply this theorem, we should differentiate with respect to force, and here we are not taking an P prime force or any other load, because we have to find deflection at free end, and here load is already exist. So if the value of 10 is given like here, we will not use the value, we will use the symbol, because we have to take the derivative and integral that way. First of all, and in the last step we will put the values. So, and if force is not here, it is applied somewhere else, then we will apply a fictitious force P prime here, a supposed force P prime here, and we will do the procedure as stated in this problem. So M is equal to minus Px, taking the partial derivative with respect to P, curly M over curly P will be minus X. So deflection, put the value here, Y will be Y, 0 to L, instead of M, minus Px is written over Ei, curly M over curly Pi, instead of this, minus X is written into dx. So minus plus X, and these things are constant taken out of the integral. P over Ei is integral from 0 to L into x square dx. When you take the integral, P over Ei will be x cube over 3, just the integral 0 to L. So overall value will be deflection at free end will be equal to PL cube over 3 EI, that we have derived from other method. So same result from here. So this is another example. Find the deflection slope of simply supported beam carrying UDL by Castigliano theorem. Just Castigliano theorem. So Y, that is formula. So what we will do, this is the beam, reaction will be find out by just applying the equilibrium condition, and then taking this section, because P1 is applied here, it at midpoint it is required, that's why P1 is required, and it is fictitious force P1, because initially there is no force is applied, it's just UDL is being acted. So P1 is fictitious force. So if it is fictitious, take two section, 1, 2. So in this section, M is this, and it is valid from 0 to L by 2, and for this section from L by 2 to L. So for X section, you will do like this, it will be the value. Remember, P1 is involved. Why? Because when you find out the reaction of this beam, RA will have P1, that's why P1 is here. So This is for section 1, this is for section y. So overall we will add up from 0 to L by 2 this. Again applying the same formula, this formula, just put the values plus same formula but from limit half of the length to full length. When you put the value you will have this, and when simplifying you will have yc 5 over 384 wl4. And for slope, at point c we have to find the slope. If that is the case, you will apply a fictitious moment m1. So when you apply here, it will have effect in reactions ra and rb. You will find that and then take the section xx. This is the value of m for section xx. Here m1 is unblurred, so you will take the derivative with respect to this fictitious moment, because now we are doing for slope, that is the fictitious moment, and partial derivative with respect to fictitious moment, and that is this value is this. For section y, taking the value, and again this will the value when you put in overall from 0 to L by 2 plus L by 2 L, and simplify you will have this, and in the last deflection is 0, and that should be 0 in the case of simplicity. So this is correct. This is called as Castigliano's theorem. Thank you very much.